Okay, so we are waiting for 5 minutes. I think so the majority of people that you assist. So first of all, thank you so much to all of us in order to see this webinar. I hope that enjoy it. So I'm going to introduce the two people that is in charge in this webinar. Okay, we are going to start with Christian De Santos, who is the CEO and co-founder of the Salk Geomechanics. Even he has a PhD in geotechnical engineering. Okay. In from other side, we have Rafael Martinez, who is the general manager of Pangea Geotecnica. It's even a Master of Science in Civil Engineering. And finally, like the more recently background, he did the Master of Science in Civil Engineering and Business Management by the Imperial College. So I am going to leave to Christian to start with the webinar. And just to keep in mind in order to establish the methodology, if you wanted to do some questions, you can use the chat when Rafael finished the presentation, or if you prefer to talk to Christian and Rafael directly, you just need to use the symbol of the hand, and then we are going to provide to you the access in order to talk to them directly. So again, thank you so much for your time, and then I leave to Christian to lead the presentation.
So Carlos, thank you for the introduction, and also thanks to all the assistants of this webinar. First of all, I would like to apologize for the cancellation of the previous webinar due to some technical issues. We hope this time everything goes smoothly, so we expect to be able to deliver the webinar, which is titled The Use of Artificial Intelligence and Pressuremeters for Optimizing Geotechnical Design. As Carlos said, this presentation is going to be delivered by myself, CEO and one of the co-founders of Salk Geomechanics, all together with Rafael Martinez, Executive Director of Pangea Geotecnia. The webinar is going to be divided in two different parts. The first one that is going to be delivered by myself, it's going to be an introduction where we will see the problem related to geotechnical uncertainty. Also, we'll see the traditional approach, how the industry have been tackling the problem of geotechnical uncertainty. And then as a last part of the introduction, our solution, our technology to overcome geotechnical uncertainty. Also, we will show some aspects of a methodology which is named back analysis or inverse analysis. And finally, some ideas about some optimization techniques that are behind the back analysis methodology, which in our case is going to be genetic algorithms. The other part that is going to be delivered for Rafael, it's going to be in three different parts. Why pressuremeters, why we are using pressuremeters, especially to obtain geotechnical characterization, different case studies where Rafael have been combining using Darwin, our tool, pressuremeter tests with Plaxis models to calibrate those models to deliver a better design. And finally, of course, some conclusions and recommendations. As Carlos said, all the questions and answers are going to be at the end of the presentation. And of course, you can interact with the chat or raise your hand, and then we'll try to activate your microphone to directly ask for your questions. So let's start. The reality nowadays is in construction, we are able to almost build everything that we can imagine of, like metro lines, cities in the middle of the desert, and even artificial islands in the middle of the ocean. However, many of those big infrastructure projects are losing money or we are paying too much for them, both financially but also environmentally. And part of the reason or part of the things that are happening that it's causing those overpayments or those overruns, it's due to geotechnical uncertainty. At the end, not knowing how the ground is going to behave, it's making that our designs are over-dimensioned. So basically, we are using more steel, more concrete, and at the end of the day, more CO2 emissions. But also, this lack of how the ground is going to behave, it's making that during construction, we suffer unforeseen events causing delays, malfunctioning, and in the worst case scenario, even the failure of our projects. And just to illustrate the magnitude of the impact of geotechnical uncertainty into our projects, here are some numbers. More than 1% of the global CO2 emissions in the world are coming due to the overuse of material related to overdimensioning caused by geotechnical uncertainty. And more than 20 billion euros with budget deviations caused by geotechnical uncertainties, and just taking into account the top 50 European construction companies. So, as you can see, geotechnical uncertainty is not only a problem for our industry, but also for our society. And that's something that we need to solve as an industry. And the reality is the industry has been tackling this problem with many different approaches. The first one, by increasing ground investigation, especially during pre-design stages, doing more laboratory tests, more in situ tests, but of course, those techniques have some limitations. Regarding or related to laboratory tests, at the end, you are altering your samples when extracting the samples from the ground, so the characteristics that you are obtaining from samples are not always representing the real ground conditions. And also we have the problem of the size of the sample. So again, sometimes the sample that we are testing is not representing or representative of the ground conditions. Regarding the in situ tests, the biggest limitation are some difficulties to interpret the results since many of those in situ tests were created in some specific conditions, and sometimes we're extrapolating the implementation of those tests in other situations. But as we will see here today, by using some of them, in this case Pressuremeter tests, in combination with other methodologies or techniques, we can overcome some of those limitations. Then, one of the other approaches to tackle geotechnical uncertainty is using sophisticated numerical tools like Plaxis, Midas, Rock Science, or FLAG that allow us to really reproduce complex geometries, complex ground behaviors, having into account ground, water, different construction sequence. But of course, if the parameters that we are introducing in our models are not well representing the ground conditions, the predictions that we can do are not going to be good. And finally, one of the last approaches that our industry is using to overcome geotechnical uncertainty, or at least knowing how the ground is reacting, is measuring the real response of the ground by installing sensors. And now at the moment, we love the word IoT, we love to put sensors, and we love to monitor the real ground behavior. However, if we take a picture of the whole life cycle of a project, we are still starting many times with poor geotechnical information that it's making us to use unrealistic parameters during our design stage, especially when using numerical models where the parameters that we are using are not representing the real conditions that we have. And it's true that we are measuring a lot nowadays, but the reality is that we are not using this data proactively to enhance our design. So we can say that there is a kind of disconnection between the reality coming from the data of the sensors with our design. So also, we can state that the industry is wasting the potential of numerical tools and missing the high value of analyzing data, especially in a proactive way. So, what we are offering is a methodology that is connecting and analyzing all the geotechnical data that we have in our projects to reduce geotechnical uncertainty. And how we do that? So in practice, we are doing that by using Darwin, our machine learning algorithm platform that the first thing that it's doing is connecting historical information, mainly borehole logs, laboratory tests, in situ tests, with predictive models, in this case numerical models, with all the data coming from IoT systems, as well as all the construction progress that is happening in our projects, as well as some data from tunnel boring machines. But today we will be focused on the functionality related to connecting predictive models with monitoring data and all the information of the construction progress, with the idea of doing automatic sensitivity analysis or parametrical analysis, as well as back analysis, using our parallel high-performance cloud computing architecture to do all of that in real time during the early stages of our projects. At the moment, our solution Darwin is compatible with Plaxis, Plaxis 2D and Plaxis 3D. So once you put your design in Darwin, Darwin knows all the different model phases that your model have, all the constitutive models that you are using, and Darwin can connect your model with the instruments, do the comparison, recalibrate the model, and show all those results in one unified platform. Of course, our system can be connected with instruments, so you need to define your instruments in our system and connect those instruments where the data is stored. That can be a server or another platform, so there is no problem. You can connect Darwin with other platforms, servers, FTP folders, or whatever. Once we define and connect the instruments and the data, the first thing that you can do is basically visualizing what the sensors are showing. The good thing is here in Darwin, one of the things that you can do once you have your design and the data, you can start comparing what the original design is saying and what the monitoring data is saying. So basically what you are seeing here is the prediction of one diaphragm wall during an underground excavation and the data coming from an inclinometer. So as you can see here, we were expecting horizontal displacements at the end of the excavation around 40 millimeters. And what the inclinometer was showing were displacements lower than 20 millimeters. And that's something that usually happens. We overestimate the ground conditions because we need to be conservative, especially when we don't have a lot of information while doing our design. What we want, what we are doing, is trying to calibrate the original design with the monitoring data in the early stages to actually characterize better the ground conditions and make sure that you can then predict what have been happening, but most important, to predict what is going to happen with lower uncertainty. Of course, a part of doing this automatic back analysis in our system on the cloud, we can run parametrical analysis because sometimes as difficult as calibrating the model is deciding what are the most influential parameters in your model. So here you can select all the parameters included in your model, run a parametrical analysis and see how the output of your model is changing while changing different parameters like cohesion, friction angle, stiffness, permeability, or whatever your model is including. But what methodology is behind the back analysis? So basically, back analysis is a methodology to calibrate mathematical models, in our case, Plaxis models, with data. Saying that for us, data in 90% of the cases is data from a monitoring system, inclinometers, extensometers, piezometers, horizontal, vertical displacement points, or some type of data coming from some in situ tests like pressuremeters, CPTUs. So basically, we are evaluating the error between a mathematical model and some data. In terms of a mathematical approach, what back analysis is is an optimization of a function, like the one that you are seeing here, which is a simple square error, where you are comparing measurement against prediction. This function can be more complicated, having to account different type of data, different type of accuracy for different instruments, so you can really complicate it as much as you want the function that you want to optimize. So as you can see, part of the success of a back analysis is using a proper optimization technique to find the zero of this function. Other results that we will show today were done with Darwin, and Darwin is using genetic algorithms to optimize this function. As a summary of what is genetic algorithms, so genetic algorithms is an optimization technique based on the theory of the evolution of the species, where basically the concept is the best individuals that are fit or are better suited for the environment, survive, reproduce, and create better offsprings. For us, an individual is a Plaxis model with a certain parameter values that we calculate, we compare with a data, so the Plaxis models with a lower error are the best individuals. So as an example, imagine that we have two parameters to calibrate, P1 and P3. The first thing that genetic algorithms require is minimum and maximum potential value and incremental value. So basically you create the search space, which are represented here by those black squares. Then you generate an initial population where those ones and zeros in red are the specific value of the parameter P1, and the zeros and ones in green are the specific values of the parameter P2. The algorithm first evaluates the error of those specific individuals, then the best with the lower error are selected, and then we apply some operators that help us to drive through the search space to find new combinations of parameters or individuals with a lower error. And we keep doing this loop until we find a proper combination of parameters that are matching what the data is showing. Again, as a synthetical and simple analysis, before going to the case studies that Rafael will show you, imagine again we have two parameters, key node, which is the relationship between the horizontal and vertical stresses, and the unloading reloading parameter. Imagine that the solution of the problem, because we know that the synthetic case study is 1.5 for the key node and 75 megapascals for the stiffness. All the ISO lines are the error, so you can see the red dot, which is the solution. First thing that we do is calculating a random initial generation, so each black cross is a Plaxis model with specific parameter values. Then we calculate all of them, we calculate the error between those models and the data, we apply the operators and create a new generation. And as you can see, generation after generation, all the black crosses are being concentrated where the minimum is. So at the end, our solution is the average of those individuals that match our criteria of being good or bad. So basically, we can say that back analysis is a way to calibrate numerical models using data, and genetics algorithms is a way to calculate hundreds or thousands different Plaxis models in a clever way. So now I will allow Rafael to show the importance of pressuremeters in order to calibrate numerical models in real geotechnical problems. So Rafael, the floor is you. You will need to share your screen and show the slides. So thanks for my part. So now, Rafael, the floor is yours. You are on mute. You are mute, sorry.
There. Thank you, Christian. So the data I will present today is the result of more than 8 years of research between industry and university, and because it deals with pressure meters, and to be honest, I know pressure meters are not very well known in the world. Not too many people use pressure meters. I'll start before showing the results of the research. I'll start with a general introduction of how pressure meters work and the historical barriers of that have prevented more people using pressure meters, which I think is very important to understand the results we will present at the end. So at the end, as I said, I'll show the results of the case studies and then some conclusions. So why we started using pressure meters and starting researching with pressure meters? I work for a company which is a design and build company. We do retaining walls, piles, micro piles, soil anchors, and we work in Chile mainly. Chile is a very seismic country, has a very different geology. We have very high mountains, 5,000 meters high in average. And then we have the sea at 0 meters. And this is separated by only 180 kilometers. So this implies that we have a very steep energy gradient, which means we don't find too many soft soils in our country. We have a lot of coarse and hard materials, which are difficult to sample and test with the standard SPTs or CPTs. Also, if we want to test unaltered soil samples to take into a lab test, that's also hard because of the big grain size we have. We normally cannot use the standard probe size because of the big grain size our soils have. So we wanted to optimize our designs. We could see that the soil properties we were getting with the standard methods were not representative of the real behavior we were observing on site when we were building retaining walls, for example. So we wanted to go beyond and do a better site investigation. And we thought in using pressure meters because it's a pre-drilled instrument. It doesn't use correlations if you use it properly, as we will show. And the instrument also mobilizes a large soil volume. Just to have in mind, a 50 mil diameter instrument is equivalent to a 1 meter triaxial probe. So that solves a big part of the problem when you have gravels, for example. And of course, the pressure meter also gives us stress-strain relationships, which is very important for retaining walls and piles. Another important thing to emphasize is that we use high-resolution pressure meters, which are different to the Menard pressure meters, which is the most common instrument. In the Menard instrument, you insert a volume of soil, of water, and that expands the soil, and you measure the pressure that is exerted by that volume. And that's a typical Menard graph you get. But this approach is mainly empirical. Normally, when you use a Menard pressure meter, you get this limit pressure and that Menard modulus, and you go into tables like this one and obtain with correlations soil parameters, like this table I'm showing here. But the problem with that method is that what you are measuring with that volume is an average deformation along the instrument. And that average deformation, you assume you have a cylinder, so you can calculate an average displacement, but that displacement will not be the same along the probe. So you lose resolution in that using that procedure. And if we want to do like a fundamental interpretation of the data, resolution is critical. This is sort of similar to what we do when we use SPTs, for example. Like nobody interprets SPTs in a fundamental fashion. Like no, you can say like with an SPT you have the mass, you have the displacement. So you could do like stress strain. You can draw a stress strain relationship with an SPT, but because the resolution of the data is so poor, and because of other problems as well, nobody interprets SPT in a fundamental way. But people go to correlations. Another similar example is what used to happen with triaxial tests. When the deformations in the triaxial were measured at the ends of the probes, people weren't getting the same results that people were measuring on site with retaining walls. And when researchers, geotechnical engineers, started measuring the deformations in the triaxial probe with strain gauges at the center of the probe, they realized that resolution, that improvement in resolution, was improving the actual data. So these are sort of analogies that we can see in our standard geotechnical practice that have to do with resolution that improve the data. The same happens with pressure meters. If we improve the resolution of the data, we improve the data. In the case of higher resolution pressure meters, the strain gauges that are normally used make the instruments 400 times more accurate than a Menard. So that sounds pretty good, but if it's so amazing, this instrument, why are not more people using it more? As I said, pressure meters are not very common. So what are the barriers? What are the problems? One of the problems is the interpretation. So if you have a triaxial element, a triaxial test, you get a stress strain curve. With a pressure meter, you also get sort of like a stress strain curve. These two curves looks pretty similar. And you can say, okay, so why don't I input this curve into a finite element software, for example? And the problem here is that with a pressure meter, you are not testing a single element, as in the case of a triaxial test. In the case of pressure meters, if we think that we are applying the pressure here inside this cavity, what we are testing is infinite soil elements. So these are infinite cylindrical elements. So what we get here as a response is the response of those infinite elements. This is called a boundary value problem. So what we get here in the pressure meter curve is the response at the end of this series of springs, if we want. And the goal of interpreting pressure meters is, if we know this integration of infinite series of springs, the goal is to understand what's happening to one of these springs. So we have to reduce this integration to what's happening to one of these elements. That's the goal of interpreting a pressure meter. So what have geotechnical engineers and researchers done along the years? They have given themselves a constitutive model, if we want, like a soil model. For example, this model, a bilinear model, or for example, Hughes in 1977 tried to solve this with a linear elastic, perfectly plastic model. And then he solved the differential equations and got an interpretation of a pressure meter curve. But of course, soil is not linear elastic, so that solution wasn't perfect or wasn't good enough. And then more researchers came along the years and then tried to improve that constitutive model and then solve those differential equations. But the problem is that as we do our constitutive models more sophisticated, the math gets more difficult. The differential equations get more difficult and difficult to solve. So unfortunately, geotechnical engineers are a bit lazy, and we don't want to be solving differential equations all the time. So I think that's one of the big barriers why pressure meters haven't got a wider use. What can be done nowadays? We can use finite elements to solve these differential equations. So we don't solve the differential equations, so a computer does it. And we can model the test. So we draw a mesh, we do the boundary conditions, we put the boundary conditions, and we have our in situ curve. And what we can do is try to iterate the soil properties so that achieving a best fit to our in situ curve. What I'm showing here is a very simple constitutive model with two parameters, phi and E dash. So it sounds easier than it is. But the problem here is that when we have more sophisticated constitutive models, for example, the HSS, the hardening soil small strain from Plaxis, it can take us 3 weeks for achieving a manual convergence to an in situ curve. We have done this with some students in a university I teach here in Chile, and this is a real time it was taking students to do this fit. The other problem of this approach is that we have non-uniqueness, which means that we can have several set of parameters that achieve the same curve. So what have we done to solve this? Darwin came to help us. We started using Darwin last year. We heard of Darwin in the context of the observational method, as Christian said before, but we said, why don't we use Darwin for interpreting pressure meters? So we started talking, and as soon as we heard that Plaxis, that Darwin was using 200 Plaxis licenses running in parallel on Amazon servers, we immediately said yes. So let's go for it. Let's try it. And the results have been impressive. We have reduced these 3 weeks time I was telling you before to 2 hours, and also the match of the in situ curve has also been improved. This is a finite element mesh from Plaxis. We are modeling a pressure meter test. The black curve is an in situ curve, and the gray curve is what the Darwin back analysis tool is giving us. So I'll go now to a case study. In order to check that we were getting correct interpretation results from our pressure meters. We instrumented 3 sites. One site was an 8.6 meter deep soldier pile wall. So we were measuring the deformations of the wall with inclinometers during the construction. This is a picture of that site. The site is has silty sands. We had 2 CPTs for this site and 3 to 4 high-resolution pressure meter tests at different depths. Then we also had 2 other sites, which were a 4-story building and also a 5-story building. And we also measured the deformations, the settlement of the foundations during the construction of each story. So the goal was to do the interpretation of the pressure meters, then model the problem and see if this approach was giving us similar result to the instrumentation. This is the first result. This thick blue line is the inclinometer. This line here is what one of the Max Jara this was a manual calibration. So this is the master thesis I was telling you what we were doing before Darwin. So a manual calibration which was taking 3 weeks for each pressure meters. So this result took us around 2 months to achieve this. Not a very good fit. This is what Darwin was giving us with the instrumentation. So this is not a prediction. This is the best approach to the soil parameters when you feed Darwin with the correct deformation measured. And this is what we were getting with the pressure meters calibrated with Darwin. So the difference is around 1 mil, 1 to 2 mil, which we think we were pretty happy with that. This is the second site, the 4-story building. The triangles are the measured settlement. Sorry, the measured settlement are the dots, and the triangles are the computed settlement with pressure meters. And this is the 4-story building, the 5-story building, and the same measured settlement is the dots, and the triangles are the computed settlement. So again, below 1 mil, the difference. In terms of the soil properties we were getting, for example, for the first site, the retaining wall site, this is a typical interpretation of one of the horizons. This is the Professor Hughes method from 1977. At the typical interpretation of a pressure meter. The Hughes method was giving us 32 degrees for the angle of shear and resistance. The CPT was giving us 40 degrees, and the pressure meter interpreted with Darwin was giving us 42 degrees. Of course, these two results are very similar and very different to a typical Hughes method for pressure meters. And the explanation of this difference is because the Hughes method ignores the elastic deformations in the plastic deforming region, which means this is what I was telling you before, like in order to solve those differential equations, people were doing simplifications of the constitutive models in order to solve the differential equations in an easier way. But those simplifications, the problem they have is that they depart away from reality. And the result of that is that the parameters you get are not realistic. So this is a 10 degrees difference. In the case of the CPT, we can rely on the CPT in this sort of geology because it's a silty sand with not too many fines. So CPTs are calibrated in calibration chambers in a similar geology. So CPT's results are reliable in this geology, and we can say that CPTs are very similar to what we were getting with Darwin. But the problem with CPTs is that if you change geology and your geology is not similar to the calibration chamber, to the correlations of the CPT, then we cannot rely on CPTs. And the big advantage here with this method is that it's pure soil mechanics. It's fundamental soil mechanics what we are doing for interpreting this. There are no correlations here. So it's just stress-strain relationships interpreted with good constitutive models. So this result means that we can extrapolate this method to more difficult geologies where we don't have correlations, for example, for CPTs. Another very interesting result we got with this research, and that is also related to these historical barriers I was talking before. It has to do with the K-naught and state parameter. And it also has to do with the insertion method of a pressure meter. The pressure meter we use is a pre-bored pressure meter, which means we do the borehole, we withdraw the drilling tools, and then we insert the instrument, the pressure meter. That means that the cavity of the soil is sort of disturbed. So people normally have said that because of that disturbance process, you cannot rely on the soil properties of a pressure meter. And it has been proven by many researchers now that if you increase the pressure during your test, because of the beauty of plasticity, what you do is sort of erasing that disturbance process. Because if you imposed a load during that insertion process, and then the load you impose because of the testing process goes above that initial load, then you use theory of plasticity and can erase or know the value you have achieved during the test. So we postulated we wrote a paper with these results. We presented it for the Pan American Conference, which was last month. And we postulated in this paper that this is a typical test. This is the black curve is the in situ curve. The gray curve is the Darwin interpretation. So we postulated that if we do our fit based on the unloading curve and also the last part of the loading, if we get our parameters at this part of the data, and then we interpolate what our data is saying to the origin of the test, we could measure K-naught and the state parameter. So that's something we postulated very carefully, cautiously in our paper. But while I was preparing this presentation, I found this very recent paper from Professor Yu of Leeds University, which is in my opinion, the most knowledgeable person in the world of pressure meters, where he is basically saying the same. If you have a pre-board pressure meter and you load the soil with a sufficient pressure that erases that initial disturbance, and then you do your fit in this last part of the loading and the unloading, you get your parameters, and then with those parameters you interpolate to determine K0 and the state parameters. So this is very important because nowadays many very important problems, for example, like tailing dams. There's a huge issue with tailing dams, what's happening with the state parameter and K0. And it's a huge issue related to static and seismic liquefaction. And nowadays, the tailing dams engineering is dominated by CPTs, and people know that those correlations are based on different geology and are trying to somehow determine the state parameters. And this could be a very important step towards refining those determination of state parameters. So in conclusion, high resolution pressure meters can be interpreted in a fundamental fashion with the aid of finite elements and Darwin. We think that this can help to overcome a historical barrier. This can be applied to any materials. We have done this with materials that would hardly qualify as soil. For example, we're doing this in a very salty, basically in salt. It's a salty rock, which there is no way of interpreting it with CPTs or SPTs or even lab tests. There are people doing this with waste, so not soil. I think there's a very interesting future there. The insertion disturbance effects can be accounted for, and even K0 and the state parameter can be determined. We are building a calibration chamber now to try to write a paper which will be presented in next year's Pressuremeter International Conference in Luxembourg to try to show this more clearly. And if you are dealing with coarse soils, also there is a big advantage because of the amount of volume we are testing with pressure meters. That's pretty much it. I'm welcome to hear questions.
Okay, so thank you so much, Rafael. So we have one question. I think so. It's I don't know if you want to answer, Christian. I think so. It's more addressed to you. I am going to read it. Darwin seems, thanks to the Mr. Weiss for your participation in this question. Darwin seems to use real-time monitoring for calibration. Has there been a situation where different monitoring systems give contradictory information? How does Darwin deal with that, or has it only been used with one type of monitoring system at a time?
Okay, so the straightforward answer is yes, Darwin and we have been facing different problems where we have different type of data or monitoring data, like displacement from an inclinometer and water pressure from a piezometer, and we can use both type of data in the same back analysis, where we can be trying to calibrate at the same time cohesion, stiffness, and permeability. So Darwin as a tool is not telling you what data you need to use. So basically the engineer, through some parametrical studies or sensitivities that they can do in Darwin, they can see what are the most influential parameters related to different outcomes. You can try to see how water pressure is changing while changing permeability or while changing stiffness or whatever. In the same way, you can check how displacements in some specific locations are changing while changing other parameters. So doing those parametrical analysis can help you to understand what is the type of data that you need to use for your back analysis. Of course, if you have contradictory data like two inclinometers, one moving to the right and the other to the left in the same project, and you actually use both of them in the same back analysis, what Darwin will try to do is to match a kind of average between the displacement from the right to the left. So Darwin is not doing that automatically at the end. Darwin is a tool to help engineers to evaluate a lot of Plaxis models in a parallel way and in a faster way, but it depends, so the quality of the results depend on the knowledge of the engineer defining a proper Plaxis model and using the proper data in terms of quality and volume.
We have another question from Daniel Peran. Could you please provide some details about the cost of the service? I imagine it depends a bit on the project, but for a Sadwell line, for example.
So for us, if you want to become a Darwin user, the first thing that you have to do is your Plaxis license to actually create your Plaxis model in your laptop. Once you have your model, you upload your Plaxis models in Darwin, and to be able to calculate parametrical analysis and back analysis in Darwin, you will need to pay a monthly subscription to access and prepare all your calculations, connect your models with the monitoring data, and then you pay a fee at the end of the month depending on the hours, number of hours of calculations that you have done doing your back analysis. Just to give you a magnitude, in terms of subscription to access, we are talking about few hundred euros per month to few thousand euros per month, depending how big your project is in terms of number of users, number of models, number of instruments, automatic data acquisition or not. And then for the calculation, it's hours per calculation. That, again, it depends on the machines that you are using on the cloud. If your model is a 2D model, a simple one, you can be paying like around 100 euros per hour. One back analysis can take between 3 to 5 or 10 hours. It depends on your original Plaxis model. But basically, to use Darwin is a subscription and then payment for usage of hours of computation.
Okay, so I don't know if someone, okay, another question from Elena Castellví. Could you please explain the calibration procedure? Does Darwin simulate the test in Plaxis? Does it take into account the test conditions, menar, self-boring diameter? Which constitutive model can it work with? Which parameters does it iterate?
Okay, so basically, Darwin and Rafael, please, at any time you think that you also can answer or give your opinion. In terms of what we are calibrating, so basically Darwin is calibrating the Plaxis model that you upload in Darwin. This Plaxis model can be representing, as Rafael showed, a Pressuremeter test or an excavation, a tailing, an underground excavation, so can represent everything you want. And then the only thing is you need to relate your model with the data that you want to use for the calibration. That can be conventional monitoring data from extensometers, inclinometers, piezometers, or actually you can use data from some in situ tests like Pressuremeters, CPTUs, and so on. So there is no limitation on that. But basically, what Darwin is doing is changing the parameters inside the Plaxis models that you upload in the system. Regarding constitutive models, we are compatible with all the constitutive models that are implemented in Plaxis, the standard ones, but also the user-defined ones. So there is no limitation on that.
Okay, we have another question more. From Daniel Peran again. Why does it only work with Plaxis? Will it be possible to work with the raw data from the sensors that we have installed? Will it be possible to make predictions with your program using the data in Excel, for example?
Okay, the reason why we are only compatible with Plaxis, it comes from the origin. In my case, part of the technology was done by myself during my PhD here in Barcelona at the UPC University. At the time, this university was collaborating with Plaxis, so I was getting familiar using Plaxis as software. And because of the relationship that I was creating with Plaxis and then with Belly, because they were seeing that we were using Plaxis in a completely different way, so not only for designing, but also expanding the use of Plaxis to construction, to optimize during construction, they were extremely supportive with us, trying to help us to make sure that we can offer this tool to implement the operational method and allow people to do those intensive analysis. So the reason is because I started with Plaxis, but also because Plaxis, Bentley, and also now the family sequence were extremely supportive with us, helping us to make sure that we can evaluate infinite Plaxis models in a parallel infrastructure on the cloud. In terms of the Excel, sorry, yes, you can use monitoring data, exchanging Excel spreadsheets with our system. So if you have historical data and you don't have a server or another platform with all the real-time monitoring data, you can exchange data in a manual fashion with no problem.
Okay, we have another question from Robbie McCall. That this is for Rafael. With regards to the pre-board Pressuremeter and the need to erase the stress history of the insertion process, have you considered using or have had experience with the self-boring Pressuremeter to achieve testing in minimal disturbed conditions? Perhaps the geology you mentioned is not suitable for it, mainly rock.
Yes, actually, the pressure meters we are using at the moment are from Cambridge in situ. And they also have self-boring pressure meters. And we have asked them to sell us the self-boring pressure meter. But in their opinion, they think that for our geology and the way we're using it is not necessary. So even in the opinion of the providers, they think that we wouldn't get any special benefits from using a self-boring pressure meters because it's a more expensive equipment, and also using it is more difficult. So it's not for free to use it. So in their words, the benefits of using that self-boring pressure meters wouldn't compensate the problems. So in summary, yes, we have thought in using it, but we have got sort of put off by the provider.
Okay, so I don't know if anyone wants to do a question. If not, I think so that we are more far away to the hour, 3 minutes. So I don't know if you want to add anything more, Christian or Rafael.
Well, yeah, I would like to publicly thank Rafael, because for us, as a small software company based in Barcelona, trying to create and deliver new digital tools, it's extremely important to test and use our technology in real projects, as Rafael did. And most important, working with people like Rafael is showing us that sometimes you think about creating a specific tool for a specific purpose, but then you find that other people is thinking to use your tool in a completely different way to do something similar. So that was a really nice journey that we experienced with Rafael. So I would like to thank Rafael and also encourage all the people today here hearing us that if they want to know a bit more about what we did with Rafael and also a bit more about what Darwin can do, we are open to chat with you guys. What we want now is to show and to prove that we can do a better engineering by using new technology and challenging ourselves, doing things different. I think that we need to change a bit how we are building our infrastructures, trying to be more sustainable, more efficient, and also more safer. So please do not hesitate to contact me, Rafael, or Carlos, because we are happy to share our experience and also learn from you guys. So thank you very much for your time today.
Thank you,
Okay.
Christian.
Okay, so thank you so much to all the people in order to participate to see this webinar. Like Christian say, we remain at your disposal if you want to answer any doubt or question that in that moment you don't know it. So just keep in mind that. Thank you so much. Thank you so much, Rafael.